Hey everyone, this is Mrs. Scott. I'm going to put together this is just a screencast of the heat of reaction notes. So if you're in period 5, you're going to use these to take notes in your notebook. And for period 7, if you missed class, you can use this to take some notes, okay? And so we've been talking about heat of reaction in terms of how we can think about it experimentally. And so what we're going to begin to talk about today is how we can think about it theoretically, okay? So if you want to create a new section in your notebook, you can. And so we're going to kind of continue how we were thinking about the heat of our reaction, our delta H, okay? So what we talked about on Monday was how we could experimentally determine the heat of a reaction. And we kind of defined that the heat of a reaction was a change in enthalpy, and we talked about how we could use calorimetry to figure out experimentally the heat of a reaction. And so there are two other ways that we can determine the heat of a reaction. One of them is using heats of formation data, and that's what we're going to talk about today. We'll begin to just talk about what this is, and then we'll talk about how you actually calculate the heat of a reaction on Monday. And then on Thursday next week, we'll start looking at bond energies. Okay. So what we are going to start looking at a lot more are heat content diagrams. We looked at these at the beginning of this unit when you took some kind of intro notes. To remind you, on the x-axis is kind of the progress of our reaction, and on the y-axis is energy. Sometimes it's called potential energy. Okay, and so we have our reactants and we have our products. And we have A is my activation energy, which for an endothermic reaction is fairly large, and for an exothermic reaction can be a little bit smaller. And so that's the amount of energy that has to be absorbed to break the bonds in my reactants. And then we have the energy that is released, C, the energy that is released when I form the bonds in my products. And so the net change in energy is B. It's that delta H, or our change in enthalpy, is the net change. We can actually see that really if this is where my reactants and products are, we can see it's the kind of difference between those two. And so if it's a positive number, we've got an endothermic reaction, and so your products are going to end at a higher spot than your reactants. And if you are an exothermic reaction, your products are going to be lower than your reactants started. Okay, and so we're going to start drawing some of these heat diagrams today as we think about heat of formation. Okay, so what is heat of formation? Sometimes it is also called enthalpy of formation, and we use the symbol H sub F, okay, which is right up here, H sub F. And so what is kind of the enthalpy of formation? So this is the amount of energy that is either gained or released during the formation of a compound from its component elements in their standard state. Okay? And so this becomes a little bit clearer as we start to talk about like some examples. But let's first define what standard state is, and then I'll talk a little bit more about this. So standard state of an element is whatever state of matter, solid, liquid, or gas, that element is at 1 atmosphere pressure and room temperature, which is 298.15 Kelvin. Okay, and so you're going to have access to this table that tells you which state of matter, solid, liquid, or gas, each element is at room temperature and at atmospheric pressure. So what you can notice is that the vast majority are solids. All of my metals are solids, and most of my semi-metals are solids as well. My diatomic gas, some of my diatomic gases and my noble gases are all gas at room temperature. And then we've got 2 elements that are liquid at room temperature, and that would be bromine and mercury. Okay, and so we can use this to determine what is the standard state of an element. Okay, and so let's say that we were looking at the compound between just say calcium and oxygen. So it would be solid calcium and oxygen gas, so O2 gas. Those would be the component elements of the compound calcium oxide. Okay. And so the heat of formation, or the enthalpy of formation, is the amount of heat, or the amount of energy rather, that is either gained or released during the formation of that compound. And so what we can say is that all elements in their standard state are known to have 0 kilojoules as their heat of formation. So if this is how they naturally occur, sodium is naturally a metal or a solid at room temperature and atmospheric pressure. Bromine is naturally a liquid. Xenon is naturally a gas. We can set that to be 0 kilojoules as their heat of formation. Okay, as in no energy needs to be absorbed or released to make that element in that state, to get that element into that state. Okay, and so we can say that anything here has their heat of formation for that standard state element is 0. So the heat of formation for O2 gas is 0 kilojoules. The heat of formation for O2 liquid, so for liquid oxygen, is not 0 kilojoules. So it matters what the state is. Okay? The heat of formation of solid aluminum would also be 0 kilojoules. Okay? And so, okay. So this table you'll be given, but you can kind of notice, you'll start to see the patterns of what tend to be solids and what tend to be liquids and gases in their natural state. Okay. Just a side note, if you notice here, all the little symbols underneath, hex, BCC, FCC, ortho, all those things, that has to do with like what structure of solid they are, how they actually are structured as a solid. That does not matter. For our purposes, we just need to know that it is a solid. Okay. So what we have is a reference chart that tells us the heat of formation for a bunch of different compounds. Okay. So the enthalpy of formation for calcium oxide, which was the example I gave before, is negative 635.5 kilojoules per mole. Okay. There's my unit right here. Okay. Kilojoules per mole. Okay, so what that means is to form calcium oxide from solid calcium and oxygen gas, O2 gas, will release 635.5 kilojoules. Okay, and so for each of these compounds, you'll notice that it says the specific compound and what their state of matter is, and then a number. And so if it is a negative value, that means that the formation of those compounds releases energy. It's exothermic. Okay, and if it's a positive number, which let's find an example here. Here's positive. NO and NO2 are both positive. If it is a positive value, that means the formation of those compounds absorbs energy. It's endothermic. Okay, and so this is a reference table that you're going to need to get familiar with. You do not need to memorize any of these things. This link right here, up here in the corner, url.mvhs.io thermoref, right up here. That is going to be your copy of this reference chart, as well as a couple of other reference charts we'll use for the rest of this unit, and that standard state periodic table. Okay. And so please bookmark this link. Okay, I'm going to link it also on Canvas. So please bookmark it. You're going to need to use that throughout the rest of the unit. Okay. So let's talk a little bit more about heats of formation and how we can think about graphing using those heat diagrams, the heat of formation. Okay. So you're going to do some practice with this. Before we jump into reactions, we're going to kind of pause and think about how we're forming compounds before we look at how those compounds are reacting with each other. Okay, so we're going to look at silver sulfide, okay, as our first compound. It's going to be a solid compound. And what we want to figure out is basically we want to write out a balanced equation for the formation of this compound from its individual elements in their standard state. Okay, and we're going to make sure to label the states of matter. Okay. And then based off of its heat of formation that we're going to get from our reference table, we're going to identify, is it endothermic or exothermic? And then we're going to graph the formation of silver sulfide as a heat diagram. We're going to show the potential energy of the reactants and products and what my delta H is, okay? And we're going to practice this with these simple equations because we're going to move on to looking at more complex chemical reactions on Monday, okay? So let's get started. You're going to do some of these on your own for practice. So let's go through 2 examples together. Okay, so Ag2S solid. So my first step is I'm going to go find that on my thermoreference chart. Okay, and so what I see right here is that Ag2S solid says negative 31.8, and so that's kilojoules per mole. So 31.8 kilojoules per mole of Ag2S are released when that compound is formed. And so I'm going to fill that in here for my HF. My heat of formation for this compound is negative 31.8 kilojoules. And so my first step is to write a balanced equation for the formation of this compound. So what are the 2 elements in their standard state that make up this compound? So I've got silver and I've got sulfur. And so I'm going to go to my table and find silver and sulfur. And here's silver and here's sulfur. And so they're both solid at room temperature and atmospheric pressure. Okay? And the only things we need to be careful of are our diatomic elements. So H2, N2, O2, F2, Cl2, Br2, I2. Everything else you can just assume it's one element. Okay? So my equation is going to be silver plus, so solid silver plus solid sulfur is going to produce silver sulfide, also solid. I need to make sure my equation is balanced. So we're going to put a 2 in front of my silver, and now I have a balanced chemical equation. So this is the formation of this compound. Okay? And so I can tell from the heat of formation, so I have overall heat is released, and so this is an exothermic reaction. So as I see this negative sign here, exothermic reaction. Okay. So what that means is that my product should be lower in energy than my reactants start out at. My reactants start out at 0 kilojoules. Okay, they're both at standard state, which means that the heat of formation for these compounds is 0 kilojoules and 0 kilojoules. And so what that means is that they're going to start out at 0 kilojoules. And so the overall change in energy is really just based on the heat of formation for silver sulfide. Okay. And so I can label on my diagram where my reactants and my products are. And so here are my reactants. My reactants are 2 silver solid and plus sulfur solid. Okay, and they're starting at 0 kilojoules because these are their standard states. Okay. The heat of formation for silver sulfide is negative 31.8 kilojoules. And so that's what we're going to end up labeling on our graph. Okay, and so here are my reactants, my product then is that silver sulfide. Okay, and so we can identify where my delta H is. It's the difference between my reactants and my products. Okay, it's not including my activation energy here. Okay, it's looking at a net change between my reactants and my products. Okay, and I can fill in this number. Where does it stop? It stops at negative 31.8 kilojoules. So the total enthalpy of my reactants is 0, and the total enthalpy of my products is negative 31.8 kilojoules. So my delta H, my change in enthalpy between products and reactants, is negative 31.8 kilojoules. What we'll see on Monday is we'll calculate the total enthalpy of products and the total enthalpy of reactants, and one of them won't be 0. And so then we'll actually have to do some calculations to find delta H. Okay. So this is an example of kind of how to graph using a heat diagram the formation of a compound. And so we're going to do one more example before we move on. Okay. So here's one more example. We've got C2H4 gas, and we're going to go through the same process. Okay. So my first step is find the heat of formation for this compound. Okay, we got C2H4 gas. On my thermoreference chart, I can see here C2H4 gas is me plus 52.3. Okay, So that's positive 52.3 kilojoules per mole of C2H4 that is formed. Okay. And so I can fill that in here for my HF. And so now I want to write out the balanced equation for the formation of this compound from its individual elements. So I'm looking for carbon and I'm looking for hydrogen. So if I look back at that table, I've got carbon and I've got hydrogen. And remember, hydrogen is diatomic, so that's actually H2 and not just H. Okay. So carbon is going to be a solid and hydrogen is going to be a gas. And so I can fill in here carbon solid and H2 gas, and that's going to form C2H4. And then my only other step here is really just to make sure this is balanced. So I have 2 carbons on this side and 4 hydrogens on this side, so I need to add a 2 in front of both of these. So because, again, my enthalpy of my reactants is 0, right? These are the standard states. I'm just looking at the enthalpy of my product, and that is a positive value here. It's a positive heat of formation, positive enthalpy of formation. And because it's positive, it's an endothermic reaction. Okay, and so what that means is that the enthalpy of my reactants is going to be lower than the enthalpy of my products. My products are going to end with higher energy than my reactants started with. Okay, and so as we fill in our table, or fill in our graph, we can add our reactants are going to be here, 2CS plus 2H2 gas. Okay, and they're starting at 0 kilojoules, right? This is the standard state of both of these. And so then I can fill in my product. My product is going to be C2H4 gas. And so where it ends is that heat of formation for C2H4 gas. Okay, and so I can also put in my delta H. So my delta H is the difference between the reactants and the products. And so here is my delta H. Again, we're not looking at the activation energy. We're just looking at the net change between reactants and products. Okay, and so my products are going to end. They're going to have a net absorption of 52.3 kilojoules. And what this diagram is telling me is that the total enthalpy of my reactants is 0 kilojoules, and the total enthalpy of my products is 52.3 kilojoules. Okay, and so overall, the change in enthalpy for this reaction is absorbing 52.3 kilojoules per mole of C2H4 that is formed. Okay, so if you can go back and listen to this again if you are a little bit confused. What you're going to do for homework is, let's see if this will, I don't think that it's not going to switch over. Okay, what you can do for homework is basically some practice with the heat of formation doing these type of diagrams. So you can either do these on slides or you can print out. There's also a Google Doc version that you could print out and do by hand. If you do the slide version, it looks very similar to these kind of examples through class. So your homework is, in addition to making sure those 6 stoichiometry problems are done, is that to also make sure that you do, I believe there are about 5 example kind of problems using heated formations to draw these heat diagrams, okay? And this is really just our first kind of step as we move towards theoretically calculating delta H for reactions. Okay. If you have questions, feel free to reach out to me over email or ask me in class on Monday. And feel free to go back and add anything to your notes from the screencast that you need. Okay. I will see you all on Monday.